Hey guys, we are starting off this chapter looking at exponential growth functions. So, an exponential growth function looks like y equals a times b to the x power, where a is not 0, b is greater than 0, but b cannot equal 1. So first thing we're going to do is just plug in some points to find our x and y values and create a graph. So if x is 3, we have 2 to the third, which is 8. If x is 2, we have 2 squared, which is 4. X is 1, we have 2 to the first, which is 2. If x is 0, 2 to the 0 is 1. 2 to the negative 1 is the same as 1 over 2 to the first, so 1/2. 2 to the negative 2 is the same as 1 over 2 squared, so 1/4. So we're going to go ahead and plot this on a graph. So at negative 2, I'm just at 1/4. At negative 1, I'm at 1/2. 0, 1, 1, 2. You can see it starts off pretty flat, but it starts to go up pretty fast. So we have something that looks like this. So as x approaches negative infinity, f of x approaches 0. That means this graph has an asymptote at y equals 0, which is this line right here. An asymptote is a line that a graph approaches, but it never touches. So it's never actually going to reach 0. And if you think about what we're plugging in here, if we plug in negative 3 for x, 2 to the negative 3 will give you 1 over 8. You're just going to get smaller and smaller fractions, but you're never going to get to 0. It's going to get very, very close. So take a minute on your graphing calculator to graph 1/3 times 2 to the x and 3 times 2 to the x, and then graph negative 1/5 times 2 to the x and negative 5 times 2 to the x, and look at that a value and see what effect it has on the graph. Go ahead and pause the video so you have time to do that. Hopefully you've had some time to look at that. The a value, one key thing to note if you didn't notice, is that it's the y-intercept of your graph. So it's where it crosses the y-axis. So you may have noticed that when you had the larger number, it increases faster or decreases faster. When a was negative, it reflected over the x-axis. Alright, so properties of y equals a times b to the x graph. If a is greater than 0 and b is greater than 1, it's considered exponential growth. A is the y-intercept, so that would be the point 0a. The x-axis is the asymptote, so y equals 0, and we just talked about that asymptote and graphed it on our graph. Domain, negative infinity to positive infinity. There's no restrictions. We can plug in anything we want for x. But range, if we're talking exponential growth, where a is greater than 0, then it's going to go from 0 up to infinity. If you're talking where the a is negative, then it would go from negative infinity up to 0 and stop there. It couldn't go past 0. So to graph y equals a times b to the x, we're going to plot the y-intercept. We're going to plot the point when x equals 1, and then we'll finish the curve with the appropriate asymptote. So here we have y equals 2/3 times 2 to the x. So I'm going to go ahead and put my graph on here. my x and y axis. So my a value is 2/3, so my point's going to be at 0, 2/3. And then when x is 1, that's 2/3 times 2 to the first. 2 to the first is 2, so 2/3 times 2 is 4/3, which is 1 1/3. So here's my graph, and here's my asymptote. There's our first exponential growth function. All right, then we have -2 times 2 to the x. So first thing I notice is that the a value is negative. So that means that this graph is going to be reflected over the x-axis. So my y-intercept is -2. And then when I plug in 1 for x, 2 to the first is 2. So -2 times 2 is -4. So that point is 1, -4. That's a whole lot steeper than our last graph. And here's our asymptote, where we approach but never reach. Okay, so then we have transformations. So transformations, we're going to graph the parent function, and then we're going to shift it. So same as we've done before with that h and that k. The h and the k is going to tell you how far. The h is going to tell you left and right. The k is going to tell you up and down, just like we've done before. So we're going to graph y equals 2 times 3 to the x. And then we're going to move right 2 and up 1 from there. So if I graph 2 times 3 to the x, my y-intercept is going to be 0, 2. And then when I plug in 1, I will get 6 out. So then when I translate that, if I move right 2, I'm at 2. If I move up 1, I'm at 3. If I move right 2, I'm at 3. If I move up 1, I'm at 7. So at 0, 2, and then 1, 6. That's what my parent function looks like. And then at 2, 3, and 3, 7. Now, one thing to note before I graph this is that my asymptote is y equals 0 here. If I've shifted the entire graph up 1, my new asymptote is going to be at y equals 1. And it may be easier for you to plot that asymptote before you try to graph so you know where your graph is approaching. Alright, exponential growth model. So in 1998, wind turbines in Europe generated about 5 gigawatt hours of energy. Over the next 15 years, the amount of energy increased by about 59% per year. Write a model giving the amount E in gigawatt hours of energy T years after 1998. About how much wind energy was generated in 2002. So, first thing I notice is that 2002 is going to be 4 years after 1998. Because 1998 would be our T equals 0. So, one thing that you need to know for exponential growth is this equation. Y equals A times 1 plus the rate of change raised to the time. So what that does is say 100% of the value plus the percent that it's increasing. So if we're increasing by 59%, we need 159% represented there. So we want to use the variable E in place of our Y here because it wants to know the amount of energy. Our A value is our starting value at 0. When time is 0, that's 1998. It says in 1998 it was about 5 gigawatt hours. So our A value is 5. And then we have 1 plus our 59%. We need to represent that as a decimal. So 1 plus 0.59 or 1.59 to the time. And then it specifically asks for when time is 4 years later. So 1.59 raised to the 4th power. So E is 31.96 gigawatt hours. All right, let's try another one of these. Write an exponential growth model that describes this situation. You purchase an antique table for $525. Each year T, the value of the table, increases by about 5%. If you think you got this, pause the video, try it on your own. I'm going to write it down for you here. So we're starting with value equals. Our initial amount is $525. We're increasing by 5%. So 1 plus 0.05 or 1.05 to the time. That's our equation. It doesn't ask us to solve for a certain year, so we're done there. Okay, compound interest has a little more complex equation here. So compound interest is the interest paid on initial investment or the principal amount and on previously earned interest. So in this case, P is our principal amount, just like it was before. It's where we start. R is our rate. N is the number of times. Notice it's in there twice. Something is compounded. And then T is still our time. And A represents our final amount after we've done all of that. So banks will use compound interest to determine how much interest they owe you. And so they can choose to compound a certain number of times a year. They can compound annually, which would be once a year. They can compound quarterly. They can compound daily. So we're going to plug into that equation and find out if we deposit $500 in an account that pays 3% interest, we want to find the balance after 2 years. So we want to find A if we put 500 in an account. We have 1 plus, and then our interest rate is 3%, so 0.03. We're compounding annually, so the number of times is once per year, and then 1 time per year times 2 years. You can go ahead and simplify any of that you want, or you can plug that into your calculator. Remember, since we're talking money, we need to round to the nearest hundredth, so we get 530 and 45 cents if we compound 1 time per year. Say we compound quarterly, so we still are starting with 500, 1 plus, and we have our interest rate of 3%, but this time we need to divide by 4 because we're compounding 4 times per year, and then raise it to the 4 times 2. So we get $530.80. So compounding quarterly gives us a little more money if they calculate that interest rate 4 times per year instead of once per year. All right, and daily, we get 500 still. 1 plus 0.03. This time we have to divide by 365 days. And then we have 365 times 2. So our rate this time would be $530.92. So obviously, the more times they're compounding that amount, the more interest you're going to make. You can see that it's not a huge difference overall, but it is a difference. All right, that's all we have for exponential growth. So if you still have questions, feel free to come in and see me. I will see you in class.